Hey students, I got a great question on this real hard one here. It's the last one in the assignment. It's from the University Physics book. It's number 89. In fact, maybe I'll just write here. It's chapter 20, but it's from our calculus book, the University Physics. It's actually volume 2. And then chapter 9, number 89. And of course, as you have discovered, the University Physics book brings us into some calculus and harder calculus. And so 89 here is a calculus problem. So let's read it here together. It says, consider a resistor made out of a hollow cylinder. And so here is the kind of the cylinder on its side. Let's see if I have anything to kind of model it. Usually I keep some little toys around here. I thought I had a cylinder somewhere. Oh, there it is. Okay. And so maybe it's looking a little bit like this cylinder. Of course, they got it kind of laying on its side here, but it's hollow in here, and it's got a perimeter, if you will, maybe I better say circumference, and there's a little thickness to it, and it looks like in the diagram that thickness is the difference between the inner radius R1 and the outer radius of R2. And so I'm going to just take a little while here to set up the problem so you kind of make sure you understand what they're asking. So considering a resistor made out of a hollow cylinder and it's made out of carbon as shown, okay? The inner radius of the cylinder, and so R sub I is 0.2 millimeters. Their notation is a little careless. They call it R1 in the picture, and then they call it RI in the wording. And an outer radius, RO, which in the picture here is R2, of 0.3 millimeters. The length of the resistor, and so here, is about 0.9 millimeters. Now, the resistivity of carbon is 3.5 times 10 to the minus 5. Prove that the resistance, and this is an important phrase right here, perpendicular to the axis is given by this value. And then, of course, what is the resistance? So part B is going to be the easy part. We're going to be able to plug these numbers into this equation and get the resistance, okay? But I also kind of want to make it clear that the current then is flowing what we'd call in a radial direction. It's flowing outward. It's not flowing along what you might think is the wire. And so coming back to here, we're not talking about going along a wire, okay? We're talking about maybe leaking from it. In fact, to try to get you to understand better, I went out to my garage and I grabbed a big bundle here of RG6 cable for my internet connection. And maybe I'll bring it close to the camera here. Probably can't focus on that close, can it? But you can see that there is an inner wire, and that's why we call this a coaxial cable, because it's got one wire in the center, kind of that dark spot in the center, then it's got some white insulation around it. Then it's got another wire, a shielding wire, and the circumference around it. And of course, then it's got some more insulation, this white plastic around it. But the point is that current, and in this case would be leaky, something I don't want in a coaxial cable. I don't want it to leak from the inner wire on radially outward to the shield wire. I want it to go, down the coaxial cable. And so we would want a high amount of resistance for something like this. And that's usually kind of where our resistance comes into play here, okay? And so that's kind of what we're after. And I say all that because if you're not careful with this problem, I think one of the first mistakes you might make, and so I just printed up, I forget the page number, but it's chapter 20, and it has this very important equation that we're going to use here. equation, 20.8, but they just, kind of derive it and describe a metal wire as the current is flowing down the wire, okay? And because the cylinder is laid out this way, you might kind of mix up the flow in this picture with the flow in this picture. And so, like I said, in a coaxial cable, there would be a center wire where it would be flowing. This one doesn't have a center wire. And that's what we would want. So we'd want that direction to have a low resistance. And then going outward to the shielding wire, we would want to be a high resistance. Now, I'm not sure if you could model your neurons this way, but that would probably be of more interest to you guys in the life science. But you would have, your data, your information going along your neurons like a coaxial cable, and you don't want it to necessarily leak out and not, stimulate the next neuron or maybe falsely stimulate a neuron. And so, you have a poke at this point that's supposed to be, the end of your finger, and it leaks out to some electricity to another neuron bunch, and so instead of being here, you think it's over there a little bit. And I know the human body doesn't always do a good job, but there's crossovers, and we have the same thing when we try to, hook a bundle of cables together in engineering, or when we try to multiplex and send about a bunch of information down the single wire. So anyways, I hope I didn't spend too much time here, but I wanted you to get a good idea of what we're talking about. And so it is the resistance of the current going radially outward, not along the axis of the radial. So not axial resistance, but what we call radial resistance. Now, the other thing that's kind of important here is then I've got to figure out how to modify and take what information I learned here in the textbook about what they had just a wire. Even though it was a cylinder in shape, it really didn't matter because they said it has a length L and a cross-sectional A. But I do want you then, as you compare this equation, these three factors that determine the resistance, the rho is the material it's made out of. And in this problem, they tell us it's carbon and it has this much resistivity. So nothing special about that term. But the L and the A are special in this sense because this resistance is L is the length at which the current is flowing. And so in the picture that you learned, it would be, along the axis. But this is why they say perpendicular. They want the flow to be perpendicular. So the flow, and therefore the L is the length going outward. So it would be, from R1 to R2, from the inner radius to the outer radius. It wouldn't be this L. And so if you're not careful with this problem, you're going to associate this L with that L, and that would be a mistake because that's not where the current is flowing. And again, that's why I thought it best to spend a lot of time here at the beginning to make sure we really understood, what this problem was asking as we make a connection back to what we were talking about and given in the lecture and how we have to kind of convert this. So I'll say it again, this L and this L are not going to be the same thing. Our L here is representing kind of this difference between inner and outer radius. It's even more complicated than that because this A is the cross-sectional area. And so in the picture in your book, it's this circle. It would be, how you cut it when you if you were to chop it, what that cross-sectional area is. But that's perpendicular to the flow of the current. And so in this case, and now that I've drawn here, let me give myself a little better, or a new drawing. I don't know about better. But since the current is flowing radially outward, and as I already mentioned then, so the L in your book equation is going to be that difference between those two. And then the area, and maybe a different color can help here. If I put this in green, and of course I just kind of drew the end, but this green piece would extend out. And so the surface area of this green cylinder is perpendicular to the current. And so the area of this cylinder is what goes here. In fact, maybe I'll use my Post-it note again here. And so if I kind of curl up a Post-it note, okay, the area perpendicular to the flow of the current is the area of this Post-it note. And so don't start putting like pi r squared here, because we want the area of a cylinder. In fact, maybe it's a good time to pause and say, okay, well, so what is the surface area of this Post-it note of this cylinder? And I think you can see that best if you kind of unroll it, because it would be its length times its width. Now, if you roll it back up, then its length is the L, okay. But this dimension is the circumference around it, so that would be 2 pi r. And then, of course, we notice that this is going to be a challenge, because this area changes as it flows outward. Coming back to this picture, when the current is near the inner radius, right here, then we can think of the area as being Ri, the inner radius. But as it flows outward, that radius keeps getting bigger, and eventually it becomes our outer radius. And so eventually the area is going to become this. So the area is continuously changing as it flows outward. And so that's where our variable, and that's where our calculus thinking is going to have to come into play here. So again, we've got some tough stuff to put together. Now, maybe another thing to put together, looking at this equation, you might do something along this line. You might think of this and split it into an L1 and an L2, so that this total L is made out of two pieces for a second. And here's why I say that. If the total resistance is equal to rho times L over the area, and the L is L1 plus L2, this helps me to conclude that the total resistance can be thought of as two pieces. Well, the first piece is the resistance of the first part of it. Maybe not half, I just cut it in two, or not necessarily in half. And the other piece is the resistance there. Okay, so now if we take all these thoughts I put together, and I hope I my little kind of mini lecture here, which took me like 15 minutes, didn't distract from the problem too much. But I need all those thoughts to put together here, because here's what I'm going to do. I'm going to say, okay, so to solve this problem, I need to figure out the resistance in a radial direction. And so kind of the first thing I would do here in solving this is to say R total is going to have to be made up of kind of an R1 plus an R2 plus an R3 plus an R4 dot dot dot, because back here, as I said, we can think of this as a bunch of pieces added together, but see, each one has a different radius. And so if you were, let me draw a new cross-sectional area here. So there's the inner radius, there's the outer radius. And so what I'm saying here is the total radius would be this resistance from this first little microscopic ring. And that's what I mean by R1. But the next microscopic ring would go around it, and that's what I mean here by R2. And again, I know I add them together. That was kind of my thinking here of why I kind of chopped it into two pieces. But the reason I had to do that is because the area, this little conversation we had here, keeps changing, because at first I had an inner radius, now I have an inner radius plus a microscopic amount, and then another microscopic amount, and another microscopic amount, and another microscopic amount, and eventually the last one is going to have this much resistance. And so in my mind, I'm doing this. I'm taking a bunch of rings, and that's what I'm representing here, the resistance of the first ring plus the second ring plus the third ring plus the fourth ring plus the fifth. And so there's an infinite number of them, and they're infinitely close together. And I would, write it, I guess, mathematically, something like this, using this formula. I would say, okay, it's the resistivity of the material time plus or times the length of it. And of course, now remember, the current's going outward. And so I'll kind of think of this ring as having a little, thickness to it. Maybe since it's kind of in a radial direction, I'll call it maybe kind of a delta R, kind of a small little radial thickness. And that's this L in my equation 20.18. And then the area, as we talked about, would be the L, the 2 pi, and the radius. Now maybe I better use a capital R for the symbols, because I've been doing that and matching the book. But like I said, this is the hard part, is recognizing these two steps, that I have an infinite sum of microscopically thin material, so the delta R, and to recognize that the delta R is the length at which the current is flowing, and that the L times 2 pi R is the area. Now, you might even call this, radius inner. And then so the second one would be rho, and, maybe it has the same thickness, delta R, but it would now be L 2 pi R. But R now would be a little bigger. If we called this the first radius, maybe we'd call that then the second radius. And then plus a rho and another thickness, delta R. and then an L and a 2 pi, and then radius 3, dot, 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 dot. Now, maybe that's best written as a summation of rho delta r L 2 pi r. Okay, that's a terrible looking sigma. And maybe to cap off our thinking is then to say, I would take the limit in my mind as I think about each of these microscopic little rings getting smaller and smaller. And now finally, after putting the ideas from the book together, and like I said, some tough ones, the fact that we got to add the resistance, the fact that we're going to add an infinite number of them, the fact that the current goes radially and not axially, is all that right there. But we finally get to something that we recognize as the second fundamental theorem of calculus, where we can replace this with the integrand dr, and then we have an L over 2 pi r, and then we can set our limits as the inner radius to the outer radius. And that by far is the hard part of the problem. It's not actually doing the calculus, but getting here, as you noticed, took me 22 minutes, and justifying each of those steps. And once you get here, now it's pretty easy. If you kind of mentally think about all these rings you're adding together and remembering from your calculus, anything that doesn't change or constants can be moved in front of the integral sign. The first thing I would do is to pull out the material, which is carbon, and say, okay, carbon is a constant. Every little ring is made out of carbon. So I pull that out. And remembering this Post-it here that was all rolled up, each little ring, if you will, would be on top of another one. And so this would kind of be like that second one I'm adding up. And then I would, add up a third one here. But as I add these all up, they all have this same length, L. Yeah, they have a different radii. Each one's a little bit bigger when it's around it, but they all have the same length, L, here. And so I'm going to use that to say L is also a constant. And then clearly 2 pi is also. And so the only thing I have is that integral of dr over r, which you can look up if you've forgotten it from your calculus class. But that's one of the ones that are pretty common, and it's the natural log of r. And then we can evaluate it from initial to final. And so continuing on with the math, I would then have ln of outer radius minus ln of inner radius. And then using the property of logarithms, where we can write a difference as a quotient, I have ln of outer radius over inner radius. So we might have to go back to our pre-calculus math class for our logarithms there. But finally we get to, I think, which is the final answer. Let's see what it said here. Yeah, he goes, prove that the resistance perpendicular to the axis is given by, and sure enough, we have the same thing. And then for B, we can just put in our numbers. And so let me grab a calculator here, and I'll put in the resistivity, 3.5 times 10 to the negative 5. Now let me divide that by a 2. I guess I'll also divide it by a pi, and I'll divide it by the length, which, let me watch my units here, because this resistivity is in meters and this is in millimeters. Let me do everything in meters. So this would be 0.1 times 10 to the negative 3. The 10 to the negative 3 would represent milli. So that's this stuff out in front here. And maybe I'll just hit enter on that. And so that's all that stuff. Now I'll go times, and then we've got a natural log. So I'll hit natural log, and then we got the ratio. And when it comes to a ratio, the good thing is we don't have to pay too much attention to our units, because the ratio, as long as they're the same units in top and bottom. So if they're both in millimeters, it would be the same ratio as if I converted them to meters. So I don't have to mess with the conversion of meters for this ratio. So I won't. I'll just take the outer radius, which is 0.3 in units of millimeters, and divide it by the inner radius, which is 0.2, and hit enter. And so after all of that, I get a resistivity of 0.0025. And I suppose if you wanted to do kind of a rough calculation, well, maybe it's too rough and I should stay away from it, but we could have said, you know, that the average area is halfway in between, and the length is the difference between them. And I'm kind of curious. And then we could have just kind of jumped right into here. We could have said, okay, the resistivity is 3.5 times 10 to the negative 5. The length that it flows is the difference between the inner and outer radius. And you can see that the difference between the inner and outer radius is 0.1. And let me make sure I put it in meters. So it's 0.1 millimeters. Then I can divide by, and so here would be the area, and if you kind of think about the radius kind of halfway between going out, and we use this formula and use kind of the average radius, we would have the length, what was the length? 0.9 millimeters times a 2 times a pi times, and if we did kind of the average radius, it'd be 0.25, again, milli. And just out of curiosity, it'd be wrong a little bit. But notice I'm really close, you know. So 0.0025 was my right answer, and my rough approximation to make my calculations a little easier was 0.0024. Actually rounds to 2.5. So it's, you know, not bad, but I'm quite sure this was involving calculus. All right, well, hope that helped. I hope I didn't babble on too long, and good luck. This was a hard one. I'm glad somebody asked about it. Take care.